Hey, guess what time it is, class? It's science time. Now take out your notes and let's get learning.
We're going to be going over something which is called molarity. And this is something that is perhaps one of the most common units of measuring concentration in chemistry. So most of the measurements that I have to do for setting up for labs, whether for high school or college, is the units are going to be of the units of molarity. So as you can see here, it's symbolized by a capital M. Don't confuse that with moles, and don't confuse that with molecules. And make sure you use a capital M for this. So definition of it here is the number of moles of solute in 1 liter of solution. Typically it's going to be of a water solution. And for short, sometimes it's called molar, just like your back teeth. So sometimes they'll say it's a 5 molar solution or a 5 molarity solution. So a lot of times when they're measuring, indicating concentration, they'll just say the word, they'll say the number and then the word molar. So again, the molarity is how many moles are there in a liter. And you have to remember, a mole is a counting unit. So it's just like saying, going back to my one fine type of graphics here. So it's kind of like if each dot represents a dozen. So 1 dozen, 2 dozen, 3 dozen, 4 dozen, and I have a 1 liter solution. So in other words, I'll be like saying I have 4 dozen and 1 liter. Well, in this case, mole is just a much larger counting unit. So it'd be like me saying I have 4 moles in 1 liter. So this would be referred to as a 4 molar concentration. So one example here, if I have a half mole, again, that's kind of like saying if I have a half a dozen of sodium hydroxide, I have a 0.5 or 0.5 molar sodium hydroxide. So you'll say the number, you say the unit, and then the substance right after that. So let's do some examples. What is the molarity of a 3.5 liter of solution that contains 90 grams of sodium chloride? All right, so before we get started, I want to do something and just try and make something a little bit more visual for you to hopefully better understand this new unit of molarity. So let's say I have a beaker, a rather large beaker, and let's say this has a volume of 3 liters. And let each dot represent a mole. And as you can see here, I have 12 dots. So a single dot would equal 1 mole. And basically all that is just a counting unit. And so just like if I were counting by dozens or by reams or baker's dozen or anything of that sort here, all it is just it represents a group of particles. So in this case here, each dot here represents 1 mole. So therefore I have a total of 12 moles right now in this whole solution. So the way to go about expressing the concentration of this is the molarity is equal to a mole per liter. So that is the units of a molarity. So for example, I have 12 moles, so I'm going to put 12 moles on top, and I have 3 liters, so over 3 liters. So as you can see here, 12 over 3, that reduces down, and that reduces down to 4 moles for every 1 liter, or perhaps more commonly written out here is 4 moles per liter. But what they end up doing here instead is they kind of abbreviate this into a unit called molarity, and they just change a mole per liter into the unit of capital M, which represents a molarity. So what this means is basically for every 1 liter you would have 4 moles. Now, if I were to take this and pour some of this into another container, so let's say I have a 1 liter container, we probably need a little bit more room here, but we'll try to make this work. So let's say I pour this. So this is a 3-liter container. That means this right here would be 1 liter, and then this right here would be another 1 liter, and this here would be another 1 liter. So if I were to pour this into this other container, pour in 1 liter, I would have those 4 dots, which would represent 4 moles. So therefore, I would have, again for the molarity, I would have 4 moles in 1 liter, or 4 moles per liter, or also called 4 molar. Now, even if you look at this, let me draw this down here. So even after I poured the solution out, I'm now down to 2 liters. So basically, what I have up here, I no longer have this. This is now inside of this container. And what's remaining behind is what I have here. And so I would have 2 liters remaining. And I would have 80 of these dots left behind. So if you look at the concentration of that, I have 8 moles left in 2 liters. And again, as you can see, this can reduce down. This will reduce down to 4 moles in 1 liter, or 4 moles per liter, or 4 molar. Now if you notice, for each one of these are all the same. Which basically means that, using the analogy of you making like a pitcher of lemonade, this would be kind of like the pitcher of lemonade. It has a certain amount of sweetness to it. It has a certain amount of sugar to it. You pour it into another cup, it's still going to have the same concentration as the sugar originally. So when we're looking at the molarity of a solution, all we're looking at is, when we say the unit of molarity, it is how many moles are there for every liter of that solution. So whether or not you have that amount or not still doesn't matter. So even if I were to take something like this and pour this into another container, and say if I poured half of it out, so now I only have half this amount here, so I have 0.5 liters. So half of it, I would only have 2 of those dots going across here. So it's kind of like if I split this in half here. So in doing so, I would have 2 moles in 0.5 liters. And again, if you look at the way this reduces down, 2 divided by 0.5 is 4. 4 moles per liter, or 4 molar. So when you pour a solution from one container into another container, if you don't do anything with it, all you're doing is you're just pouring into another container. The concentration remains the same all the way through. So hopefully that you can understand that later on when we start getting into dilutions. We want to take this one step further and eventually get to the point where you pour into another container, but then you bring the volume up with some extra water and see what happens to it. But when we start getting into the calculations with the molarity, all we're looking at is basically just how many moles are there within a given volume of a liquid. Most often it's going to be water. So let's take a look at the first example problem. And so to keep this in the back of your mind is that when we're looking at molarity, we're just looking at how many particles given within a certain amount of space. All right, so let's work this out. All right, so for the first problem, we're trying to find out the molarity of salt into sodium chloride. So for number 1, and the key thing is that molarity is equal to a mole per liter. So always remember, we need the unit moles and we need the unit liters. If we don't have either one of these, we may end up having to do some conversions in order to get to those units. So then ultimately you can find out the molarity. Or in some cases, if you know the molarity, you may have to work backwards to find out like the number of moles or how many liters or even how many milliliters. All right. Now, one thing that is going to be helpful is looking back at this flow chart. Remember this? Where we had the grams to moles, moles to grams. We're going to be using that from time to time. So just a reminder, whenever we're going from grams to moles, moles to grams, we either have to use a periodic table or you have to use the formula weight. And the values you end up getting here, your conversion units, are the X number of grams is equal to 1 mole, which allows you to either put grams over mole or mole over grams. So when you're looking at moles over here, we need this unit. So if you have grams, you can find moles. Or in some cases, if you have moles and it's asking what is the mass or how much does something weigh, you have to use the moles to find the grams. And the same thing with the liters. You might have a unit in milliliters, but you need to convert that into liters or vice versa. So let's take a look at the first one. Since we're dealing with sodium chloride, one thing I would recommend doing is write down your units here. So we have molarity, moles, and liters. Okay, so we have 3.5 liters, and we have 90 grams. And we're trying to find out what is the molarity, what is the concentration of it. So we don't know that, but we have 90 grams. So if you look at this, we have the unit grams, but we need to find the unit of moles. And again, it goes back to this. We have grams, we need to go to moles. We need to use the formula weight because we're dealing with a compound of sodium chloride. So before we can do that, sodium chloride, so 1 mole of NaCl. So if you have 1 mole of sodium chloride, you're going to have 1 mole of sodium and 1 mole of chlorine. And so we need to find how much does sodium chloride weigh. So if you look at the periodic table, now I end up using like the Ashland University periodic table. If you have the one where it was the Xerox copy of it, you can use that one as well. The numbers might be a little bit different, but that's okay. So we need to find out the formula weight of it. So 9898 grams for every 1 mole. And for chlorine, 35.4527 grams. Again, your periodic table might be a little bit different. As long as it's pretty close to it, you should be okay. So you better not use a calculator on this. So this would be how many grams of sodium would be in there, and also 35.4527 grams of chlorine. And then we're finding out the total mass, which comes out to be 58.4425 grams is equal to 1 mole of NaCl. Which, what we've just done is we just figured out this part right here. So 58.4425 grams, that's your X value, is equal to 1 mole. So this is going to become a conversion unit for your 90 grams. So now we have the 90 grams over here. So we need to use the 90 grams. I want to use this inside the set of parentheses to find out how many moles of sodium chloride do I have. So technically this is over 1. In order to get rid of the unit grams, I need grams on the bottom. So 58.4425 grams underneath 1 mole. This way grams will cancel. You end up getting about 1.46 0.54 moles of sodium chloride. So now we have the number of moles. So 90 grams of sodium chloride is 1.54 moles. So now we can go ahead and figure out what is the molarity. And using this formula right here, so molarity is a mole per liter, and the moles is 1.54 moles. And the volume is 3.5 liters. So when you divide it out, you end up getting 0.44, and technically the unit would be a mole per liter, but they redefine that as 0.44 molar. So that is your answer. So you have a 0.44 molar, and I should put underneath here, sodium chloride. Okay, so that's the concentration. So that means for every 1 liter of sodium chloride, you would have 0.44 moles. Now keep in mind, this is a grouping. It is possible to have a fraction of a group, just like it's possible to have a half a dozen. 0.5 dozen is still 6 eggs. Or it's even possible to have a quarter dozen. So this is representing a quantity of particles. All right, so let's move on to the next one. 2a. How many moles of hydrochloric are present in 0.8 liters of a 0.5 molar hydrochloric? All right, for number 2. Number 2 has 2 parts to it. So you're trying to find out how many moles are present in 0.8 liters of a 0.5 molar hydrochloric. So again, one thing I would recommend doing is just write down the information that you have. So you have molarity, moles, and liters. Those are the 3 main things that you'll need. So it's asking how many moles would you have. So we don't know that. But you have 0.8 liters, and also you have a 0.5 molar. Okay, so now if you look at the equation, molarity is equal to a mole per liter. So now we're trying to solve for how many moles do we need. Now moles is already on top. It's being divided by liters. We need to get rid of the unit liters. So the only way you can do that is multiply both sides by liters. This way over here, liters will cancel out. So therefore, a mole is equal to, you want to take the number of liters times the molarity. So let's go ahead and plug in the numbers. So a mole is equal to the liters, which is 0.8 liters, times the molarity, which is 0.5 molar. Right, now, if you look at the numbers of this, you have 0.8 liters and 0.5 molar. Now, if you look at the units, a liter and molarity doesn't look like anything really is going to be happening with this. Now, the reason why something is going to happen with this, because it looks like the unit should be a liter molarity or molarity liter. But you have to keep in mind, a molarity is a mole per liter, which means that this is actually 0.5 moles over liter. Now, look what happens here. Technically, this is over 1, which means liters is on top, liters is on the bottom over here. Liters are going to cancel out. You're going to be left with the unit moles, which is what we're trying to solve for. So a mole, so 0.8 times 0.5 is 0.4, and the unit left over is moles. So that's your first part of your answer here. So you're going to have 0.4 moles of hydrochloric. So that was number 2, part A. Part B, how many grams of hydrochloric were dissolved? So for part B, this is now where we have to go back to this. We now have the number of moles, or here on the chart. We need to need to get to the unit of grams, or the mass of it. In order to go from moles to grams, we need the formula weight. So, since we're dealing with hydrochloric acid, we need to find out what is the formula weight for hydrochloric acid. So 1 mole of HCl, so if you have 1 mole of hydrochloric, you're going to have 1 mole of hydrogen and 1 mole of chlorine. Right, so moles to grams, you have to look on the periodic table. Hydrogen has a mass of about 1.0079 grams all over 1 mole. And chlorine is 35.4527 grams for every 1 mole. Better not use a calculator again. So you have 1.0079 grams of hydrogen and 35.4527 grams of chlorine. So the total mass, so you're just taking the weight of all the individual parts, comes out to be about 36.4606 grams, is equal to 1 mole of hydrochloric. And basically all you did right now is you just solve for the X number of grams. So this right here is going to become your conversion units for this part. So now, once we have that, we can take the information from the 0.4 moles and use this information inside the parentheses. Now, since I have the unit moles, this is technically over 1. I need moles to cancel out. So I need to put the moles on the bottom. So I'm going to put 1 mole of hydrochloric on the bottom, and I'm going to put the mass on top, 36.4606 grams. This way, moles will cancel. And if you take 0.4 times 36.4606, you're getting 14.5842 grams. You really don't have to take it out that far here. Typically, like on your Moodle homework, when you start doing this, you want to take it about 3 non-zero digits past the decimal point. So in this case here, I took it about 4 places. So that is your answer for this part. So if you're trying to make a solution of hydrochloric acid that is 0.5 molar and you need 800 milliliters or 0.8 liters, basically you just figured out how many grams of hydrochloric has to be dissolved in order to produce this concentration within this volume. Oops, if you can see the concentration here, this concentration in this volume. All right, this is something that a lot of times whenever I'm preparing a solution, this is the type of work that I have to do in order to figure out the correct types of concentration needed for various types of labs. All right, so let's move on to the next one. Number 3. How many liters does it take to dissolve 10 grams of sodium hydroxide to make a 0.1 molar sodium hydroxide solution? All right, number 3. Now for number 3, so you have 10 grams of sodium hydroxide, and you're trying to make a 0.1 molar solution. You want to know what is the concentration of it. So again, let's write down the 3 here. Molarity, moles, liters. All right, so you have 0.1 molar. Want to know how many liters would that be? So we don't know that. And we have 10 grams. Well, we don't have grams, but one thing that can be done is you can convert the grams into moles. So I'm going to put the 10 grams over here. But we need to get this into a unit of moles. So again, if you look at the information we have here, we're trying to solve for how many liters, but we need to get this into a unit of moles. So with the sodium hydroxide, we need to find the formula weight. So again, we're going back to this. we have 10 grams. I need to know how many moles. I need the formula weight. So for 1 mole of sodium hydroxide, I need to find out what is this value of X here. So 1 mole of NaOH, I would have 1 mole of sodium, 1 mole of oxygen, and 1 mole of hydrogen. And then using the formula weights for each one. So sodium is about 22.9898 grams over 1 mole. Oxygen, everyone together, 15.9994 grams for every 1 mole. And for hydrogen, it's 1.0079 grams for every 1 mole. Again, better not use a calculator on this one here. So at 898 grams of sodium. We have 15.9994 grams of oxygen and 1.0079 grams of hydrogen. So we have the weight of all the individual parts of sodium hydroxide, and when you add them all up, it comes out to be about 39.9971 grams. It's equal to 1 mole of sodium hydroxide. So it's almost 40 grams for every 1 mole. So now, that is your conversion unit. This is what's going to be put inside the parentheses. So you have 10 grams. So now I'm going to take 10 grams sodium hydroxide. I'm going to put this inside the parentheses. But this is all over 1. Grams is on top. To cancel it out, I need grams on the bottom. So I'm going to put 39.9971 grams on the bottom, and then 1 mole on top. This way grams will cancel. And when you do that, you end up with basically 0.25 moles. Not exactly here, it's a little bit greater than that, but all intents and purposes is 0.25 moles of sodium hydroxide. So now I have my answer that I need for here. So 10 grams of sodium hydroxide is basically 0.25 moles. So now I need to go ahead and solve for how many liters is that going to be. So again, a molarity is equal to a mole per liter. But I need to solve for liters. My unknown is in a denominator. I need to bring this up to the top. So the first thing I need to do is multiply both sides by liters. This way liters over here will cancel out. So I end up with liters times molarity is equal to moles. Now, liters is on top, but it's being multiplied to molarity. I need this by itself. So I need to divide out the molarity. So over here, the molarity will cancel out. So the liters is equal to a mole divided by molarity. So my moles is 0.25 moles. Oops, if you can see that. Okay, so my moles is 0.25 moles. And the molarity is 0.1 molar. Okay, now again, if you look at the unit for molarity, a molarity is actually a mole per liter. Because if you look at this, it looks like the unit should be a mole per molarity. So let me rewrite this here. 0.25 moles. And the molarity is 0.1, and the molarity is actually a mole per liter. So what happens here is moles and moles will cancel out. You're actually left with a 1 over 1 per liter. The very bottom denominator comes up on top. If you remember from a while back, I was going over like 1 over 1/4 is equal to 4. Or 1 over 1/3 is equal to 3. 1 over 1/2 is equal to 2. In this case, 1 over 1 per liter is a liter. So the same thing happens with this. So 0.25 divided by 0.1 comes out to be 2.5, and the units for that is liter. So that means to make a 0.1 molar solution, and if I have 10 grams of sodium hydroxide, which is 0.25 moles, I need to use 2.5 liters to give me that concentration. Right. Any questions on that? If you do, let me know. Let's try another one. Number 4. How many liters does it take to dissolve 4 moles of nitric acid, which is HNO3, to make an 8 molar nitric acid solution? And for number 4, again, you're trying to find out how many liters that you need to use. So start off with molarity, moles, and liters. And just put in the information that you have. So in this case, we have 4 moles, and we have an 8 molar solution. I'm going to know how many liters is this going to be. This one's going to be pretty straightforward here. So we already have all the information we need. We just need to solve for liters. So molarity is equal to a mole per liter. So since we're trying to solve for liters, down here, we need the unknown on top and stand by itself. So liters is on the bottom, and it's being divided by the moles. So first of all, we need to bring this up to the top. So the way you can do that is multiply both sides by liters. So liters over here will cancel out. You're now left with a liter times molarity is equal to moles. Now liters is on top, it's being multiplied to the molarity. You have to make this stand by itself. So to get rid of molarity, we need to divide out the molarity. This way, molarities will cancel out. So a liter is equal to a mole divided by molarity. So it's just a matter of just plugging in the numbers. We have 4 moles, and we have an 8 molar solution of nitric acid. Now, if you look at the units, it looks like nothing is going to happen, but this would be a good time to go ahead and convert molarity into its actual units, which is 8 moles per liter. And again, moles will cancel out, and we're going to be left with liters. So it's actually 1 over 1 per liter. So 4 divided by 8, let me put this down here. 4 divided by 8 is 0.5. The unit left over is liters. So it would be a half a liter. So that means if you were to take 4 moles of nitric acid, HNO3, and put it into 0.5 liters of water, you will have an 8 molar solution. So that gives you the concentration of it. Now if you end up taking Chem 2, one thing we can also do with this is that we can also determine what is the pH. So there's some other things later on that this can lead down into. So, but that's a topic for another day. So let's move on to the next one. Number 5. What is the molarity of a solution composed of 5.5 grams of potassium iodide dissolved in enough water to make a 0.125 liter of solution? So to start this one off, let's always do what we've always done here is just write down your givens. So you have molarity, moles, and liters. And then plug in the information you have. So you're trying to find out what is the molarity. So we don't know what that's going to be. We have 5.5 grams. Well, we don't have grams, but grams can be converted into moles. So I'm going to put that information over here. 5.5 grams. And 0.125 liters, which is 125 milliliters. So we need to find out what is the molarity of it. And again, we have the liters, but we need to convert the grams into moles. So we need to use the formula weight. Because this is potassium iodide. Now don't confuse that with the potassium iodate. Potassium iodate is KiO3. This is potassium iodide, which is just simply Ki. This is +1, this is -1, so the charges balance out. So we need to find out what is the formula weight for potassium iodide. So if we have 1 mole of potassium iodide, you're going to have 1 mole of potassium and 1 mole of iodine. And then using the periodic table, potassium is 39.0983 grams for every 1 mole. And iodine is 126.9045 grams for every 1 mole. May not have enough room here. So that gives me 39.0983 grams of potassium and 126.9045 grams of iodine. Add these two values together and end up coming out to be 166.0028 grams is equal to 1 mole of potassium iodide. So this is what's going to be the conversion unit. This is what I'm going to have to put inside the set of parentheses. So I need to convert the 5.5 grams using this to find out how many moles are there. So let's go ahead and work that one out. So if I have 5.5 grams of potassium iodide, again, technically this is all over 1. So I need to put 1 mole on top and 166.0028 grams on the bottom. This way grams can cancel out. And when you do that, you end up with 0.03313 moles. All right, now let me go and put this up here. So 0.03313 moles. So now I have my moles and I have my liters. I just need to solve for the molarity. So molarity is equal to a mole per liter. So just plug in the numbers. The moles is 0.03313 moles, and this is dissolved in 0.125 liters. All right, so when you divide it out, you end up getting 0.26506 moles per liter, which is the same thing as 0.26506 molar. And this is of potassium iodide. So if you dissolve 5.5 grams of potassium iodide in 125 milliliters of water, or 0.125 liters of water, this will be the concentration of the potassium iodide. And basically what that means is that for every 1 liter of potassium iodide, you would have that many moles of potassium iodide dissolved within it. All right, let's move on to the next one. 6a. How many moles of sulfuric acid are present in 0.5 liters of a 0.15 molar sulfuric acid solution? All right, for number 6, we're dealing with sulfuric acid. And again, start with what's given to you. You have molarity, moles, and liters. All right, so in this case, we have, at least for part A, this is for part A here, we have a 0.15 molar solution, and you have 0.5 liters. So the first part is asking how many moles do you have? All right, so now we have the molarity, we have liters, and we can go ahead and solve for moles. So molarity is equal to a mole per liter. We want to know how many moles are there. So we want the unknown to be on top and by itself. So it's already on top, but it's not by itself. So we need to get rid of the liters. So you need to multiply both sides by liters. Liters will cancel out. So you end up with a mole is equal to the liter times molarity. So we have the liters, we have the molarity. We're just going to plug those two values into this. So a mole is equal to the liters, 0.5 liters, times the molarity, 0.15 molar. And again, a 0.5 liter, and the molarity is actually a 0.15 mole per liter. Now this is all over 1, which means liters is on top and liters is on the bottom. These two liters will cancel out. It's going to be left with the unit of moles on top, which is what you want. So for part A, 0.5 times 0.15 comes out to be 0.075 moles, and this is of sulfuric acid, H2SO4. So that's your first part of the answer. Now for part B, we're going to take this one step further. Part B, how many grams of sulfuric acid are present? So for part B, it's asking how many grams, or the mass of the sulfuric acid. And this is where we go back to this. So we have the moles. We need to find out how many grams. So we need to find the formula weight. So we need to find the conversion unit, or the formula weight for sulfuric acid, in order to go from moles to grams. So for sulfuric acid, if you have 1 mole of it, this means you would have, for every 1 mole sulfuric acid, you're going to have 2 moles of hydrogen, 1 mole of sulfur, and 4 moles of oxygen. We need to use a periodic table. And hydrogen has a mass of 1.0079 grams for every 1 mole. Sulfur is about 32.066 grams for every 1 mole. And oxygen, everyone together, 15.9994 grams for every 1 mole. All right, so moles will cancel. We're left with the unit grams. So therefore, you're going to have 2.0158 grams of hydrogen. You're going to have 32.066 grams of sulfur. And also you're going to have 63.9976 grams of oxygen. So you have basically the weight of all the different parts. To find out the weight of the whole thing, add everything together, and it comes out to be about 98.0794 grams is equal to 1 mole of sulfuric acid. Okay, so this is going to be your conversion units. This is what's going to go inside the parentheses. So you have the moles. So you have the 0.075 moles. Using this as your conversion, if you can see it here, using this as your conversion, you're going to go from moles to grams. So you're going to take 0.075 moles. Now, this is all over 1. So in order for moles to cancel out, I need moles on the bottom. So I'm going to put 1 mole on the bottom and 98.0794 grams on top. This way moles will cancel out. And so 0.075 times 98.0794 794 comes out to be about 7.356 grams of sulfuric acid. And that's your answer for part B. So what that means is this. If you need a 0.15 molar concentration of sulfuric acid, and you want to make it in a 0.5 liter container, what needs to be done is this many grams of sulfuric acid needs to be dissolved into this volume of water to give you that concentration of solution. And this is something that, again, I have to do quite a bit whenever I'm preparing the solutions here, is that I need to take into account if I need to have a certain concentration and I need a certain amount of it, how much do I have to dissolve in order to give me that concentration and that volume. So if you have any questions on that, send me a message, and later on there will be a Moodle assignment that's going to be related to that. All right, the next thing we're going to be getting into is how do you go about making dilutions. So we'll stop here for now.